In this lecture, I want to talk a little about the convergence and the rate of convergence of a numeric method. Let's, before everything, I define some concept about the error. Look at this definition. We suppose that the sequence of Pn from 0 to infinity converges to P, okay, and let Pn be not equal P for all n. If there exists a positive constant number, we call it lambda, this one, and there exists an alpha such that the limit of absolute value of Pn plus 1 minus P over Pn absolute value of Pn minus P to power of alpha when n goes to infinity be equal to lambda. Then we say that the sequence of Pn converges to P of order alpha, okay, and we call lambda the asymptotic error constant. So these two concepts are very important when we want to talk about the order of convergence, a numeric method. Okay, there is some facts about this formula, about this limit. The first one is that when alpha be bigger, okay, for example, alpha be equal to 2 or 3 or 1, every number can be alpha. When alpha is a bigger number, the rate of convergence is faster. But lambda is not as important as alpha. It has some effects, but it's not too important. In some special cases, if alpha is equal to 1 or alpha equal to 2, okay, for example, when alpha is equal to 1, the sequence is linearly convergence. It means that the rate of convergence is linear. And when alpha is equal to 2, the sequence is quadratically convergent. It means the rate of convergence is quadratic. It's clear that the convergence of the second order is faster than the convergence of first order. And when alpha is less than 1, we call that the sequence is sublinearly convergent. It's very slow, in fact. We do not like the sublinearly convergent sequence. But for alpha equal to 2 is, in fact, the best rate of convergence. Of course, if alpha will be equal to 3 or 4 or more than 2, it's okay. But usually we use the quadratic convergent in Newton method, and we will talk about it later. Let me show you the concept of linear and quadratic convergence. Consider a sequence Pn, n from 0 to infinity, and let Pn is linearly convergent to 0. Okay, so by the definition of the rate of convergence, limit n to infinity, absolute value of Pn should, in fact, it should be Pn minus P, but P is equal to 0. So this will be just absolute value of Pn over absolute value of Pn to power of alpha, and alpha will be 1 here because we told that Pn is linearly convergent to 0. So this is true. And let P tilde Pn tilde for n equal to 0 to infinity is quadratically convergent to 0. So by the same definition of the rate of convergence, we will have limit n goes to infinity, absolute value of Pn plus 1 tilde over Pn tilde squared. In fact, these two will be alpha for the quadratic convergence. It will be half. Okay? Now, let me ignore the limit term and just we say the absolute value of Pn plus 1 over Pn is approximately equal to half. And absolute value of Pn plus 1 tilde over absolute value of Pn tilde squared is approximately equal to half. From this one, we get Pn minus 0 equal to, in fact, here Pn plus 1 we know is Pn minus P0. Okay? So Pn minus P0 is equal to Pn, and it will be, if we multiply both sides in absolute value of Pn, we get Pn, absolute value of Pn, approximately equal to half absolute value of Pn minus 1. And we repeat this process for Pn minus 1. In fact, we know Pn minus 1 absolute value is approximately half times Pn minus 2. Okay, and we get, instead of Pn minus 1 here, half dot Pn minus 1, something like this. We will get half squared, absolute value Pn minus 2, and if we repeat in the same way, finally we get absolute value of Pn approximately equal toch to power of n times absolute value of P0. This is for linearly convergence. Okay? Now, for the second one, for the quadratic convergence, you consider exactly the same things. Pn tilde absolute value is equal to, from here, we get Pn tilde approximately equal to half times Pn minus 1 tilde squared. And here, if we put instead Pn minus 1 tilde, half Pn minus 2. Okay, so we will get half times half Pn minus 2 tilde squared. We will get half squared here, times half is half to the power of 3, and absolute value of Pn minus 2 tilde to power of 4. Okay, and if we continue in the same way, and in fact we put, instead of Pn minus 2 tilde, we put half absolute value Pn minus 3 squared. We put here, we get half times half to power of 4. We will get finally half to power of 7. Absolute value Pn minus 3 tilde to power of 8, and so on. Okay, so finally we get absolute value of Pn tilde is approximately equal to half to power of 2 to power of n minus 1 times P tilde 0 to power of 2 to power of n. And this means that the rate of convergence in the second sequence is much faster than the linearly convergence, in fact. So you can see the concept of linear and quadratic convergence in this example. And if we implement, for example, a numerical method to finding an approximation for Pn, okay, with linearly convergence, we get this number in the 7 first steps. Okay, this is in fact the error, for example. The error in the first step is half times 10 to the power of minus 1. And finally, in the seventh step, we will get 7.8125 times 10 to the power of minus 3. But if we implement the same a new numeric method to finding the approximate with a quadratic sequence, okay, we will get this result for the error term. In fact, in the first step, we have the same error as the linearly convergence. But in the seventh step, the error will be much smaller than the other one. Okay, it's 5.8775 times 10 to the power of minus 39, and it will be very small number. So you can see that the effect of the quadratic convergence, okay, in compare of the linearly convergence. But we have a very important theorem that the first part of theorem have been proved in the previous lectures. Let me repeat some parts of the theorem. Let G be equal to, in fact, we want to find the rate of convergence of fixed point iteration, and we want to show that the rate of convergence for the fixed point method is 1. Okay, so let G be a function is C of A and B. It means G and G prime are continuous, and they lie in the interval A and B. Okay, such that G of x belongs to A and B for all x in A and B. And suppose that G prime of x is continuous on A and B, because we say G is belong to C of A and B, and there is a positive constant K less than 1, so that absolute value of G prime of K is less or equal K for all x in the interval, in the open interval A and B. Now, if G prime of P star is not equal to 0, then for number P, for any number P0 in A and B, the sequence Pn equal to G of Pn minus 1. In fact, this is the fixed point sequence. If you remember, this is the fixed point sequence. This says that the convergence only linearly to the unique fixed point P star in the interval A and B. Okay? Now, for the proof of this equation, the first part, in fact, the existence and the uniqueness of the fixed point theorem have been proved in the previous lectures. It just remains, we prove that, in fact, we have to prove that limit Pn plus 1 minus P star over Pn minus P to power of 1 equal to something lambda. Okay? We have to prove something like this. So, let's start with Pn plus 1 minus P star, okay? And we put instead of Pn, G, Pn, and we put instead of P star, G, P star, because we know that P star is equal to G P star. In fact, P star is the fixed point of the function G. Okay, now we use the mean value theorem, and we know that there exists a Cn in the Pn and P star interval such that G prime of Cn is equal to Pn minus P star. Okay, now if Pn goes to P star, then Cn is between Pn and P star, and we must also have Cn goes to P star. Now, since G prime in any point in the interval is continuous, so we get limit g prime cn n goes to infinity is g prime of p star, and then we can in fact here if we get absolute value here, we get pn plus 1 minus pn, and here if we get absolute value something like this, okay, and we divide both sides by pn minus p star, absolute value pn minus p star, we get something like this. In fact, we get pn plus 1 minus p star over absolute value pn minus p star. Okay, this will be absolute value of g prime c n. Now we get limit both sides and we goes n to infinity. Okay, so we will get limit absolute value pn plus 1 minus p star over absolute value pn minus p star, and n goes to infinity. It will be limit of absolute value g prime of cn n goes to infinity. But from here we know that this limit is equal to g prime of p star. From here we put here. Now if we consider alpha equal to 1 and lambda equal to absolute value of g prime p star, so in fact we get the definition of the rate of convergence, and since alpha is equal to 1, so we can say that the rate of convergence of the fixed point method is only 1, and in fact it's linear convergence. Okay, now there is a very important theorem, but we do not prove this theorem. Before the theorem, just let me say that if we want to have a quadratic convergence for a sequence, in fact we have to construct and we have to design in fact a function g such that g prime of p star is also equal to 0. Okay, so let me have a look to this theorem. Let p star be a solution of the equation g of p equal to p, and let g prime of p star is equal to 0, but g second of x is not equal to 0, but it is continuous and strictly bounded by m on an open interval. Okay, now there exists a delta such that for every p0 in p star minus delta and p star plus delta, the sequence defined by pn equal to g of pn minus 1 converges at least quadratically to p star. Okay, this is a very important theorem, but we want to use this theorem in fact to find the Newton method again, but in a new way. In fact, in the previous lectures we determined the Newton method by Taylor formula. Okay, but here we want to use this theorem and we want to construct the Newton method again. Okay, we want to solve this equation f of x equal to 0, and we want to use the fixed point iteration. We know that the fixed point iteration is linearly convergent. Okay, but if we consider g of x something like this, okay, in fact we consider g of x equal to x minus phi of x f of x, and we want to solve x equal to g of x, and we let phi of x is differentiable. In fact we can find derivative of phi of x. Now if we can find phi of x such that g prime of p star be equal to 0, okay, so f of p star will be also 0, but the rate of convergence for this fixed point problem is at least quadratic. Now, let me try to do something. In fact, I told you we have to find phi of x such that g prime of p star be equal to 0. So let's take derivative from both sides of the g of x. In fact, we compute g of x equal to, look at here, if we compute the derivative of x, g prime of x, in fact, equal to 1 minus phi prime of x times f of x minus phi of x times f prime of x. Okay? We will have something like this. Exactly this one that I have written here. Now, at x equal to p star, okay, if we compute, we know that f of p star is equal to 0. Okay, so we compute g prime of p star here. It will be 1 minus phi prime of p star, f of p star, phi of p star, f prime of p star. Okay, we know that f of p star is equal to 0. So all of this term will be vanish. Okay, so we have just 1 minus phi of p star times f prime of p star, something like this. Now, if we want to have the quadratic convergence, okay, g prime of p star should be 0. So if I put this equal to 0 and solve it for phi of p star, so phi of p star will be 1 over f prime of p star, something I have written here. Now, if we define g of x, look at the previous slide, we define g of x equal to x minus phi of x times f of x. So if we put instead of phi of x 1 over f prime of x, we will get g of x equal to x minus f of x over f prime of x. Now here, if you define a sequence like this, xn plus 1 equal to xn minus f of xn over f prime of xn. Look at this sequence. Isn't it familiar for you? Exactly. This is familiar. This is, in fact, the Newton sequence to finding the root. In fact, we derived the Newton method again, but in a new approach. So, in the next lecture, I will solve some problem in this, in fact, for this subject, and I will try to show you how to compute the rate of convergence for some sequences. Follow me please in YouTube and subscribe my channel, and please introduce my channel to your friends. Thank you.